been working on this topic of noise in software engineering context for quite some time now. I remember the first time when we were introduced to this topic, we were testing the effectiveness of a machine learning-based method for optimizing software regression testing. And at that point in time, we found a lot of entries in the data we had to be duplicates, and they came with different class values. We did not realize that this is called noise. At that point, we thought that these are unwanted entries that we should handle somehow. We didn't know how yet. So we thought, okay, let's examine the effectiveness of those, the impact of those entries in the data on the predictive performance of the model for regression testing. So we ran a few experiments at that point, and the results gave us clear indication that noise or those entries are actually detrimental on the predictive performance of the model. So we said, okay, the question then that sticked out was, okay, so how do we treat such entries in the data? What is the best way to treat them? And if you look into the software engineering literature, you look into the software engineering literature, you'll find a lot of studies that utilize machine learning for solving different software engineering tasks, such as defects prediction, software cost estimation, and other things. But what was surprising is that very few authors actually addressed the problem of noise before they used the data for training a machine learning model. So we thought this topic is somewhat neglected a little bit in the software engineering literature, and it's worth exploring more. But what is class noise? So that's the question first. I mean, I define it broadly, but I'll go into now an example from a software engineering practice to make it more clear. So if we had a code check-in made by a developer and we have two reviewers looking at this code, and that reviewer one thought that this code cannot be merged because there's a stylistic problem in the code, and the reviewer two thought that, okay, this code works well and it's ready to be merged. And if we were to use such data set for training a machine learning model to, say, predict stylistic issues in the code, then we'll end up with a data set that looks like this. We'll have exactly half of the lines split between disapproved and approved because we use the sentiment of the reviewer there to label each line of code that we have. So you see here that lines 7, 8, 9, and 10 in both training examples, they're contradictory. That's what we call contradictory because they're exactly identical, but they come with different class values. Okay, so how do we treat such entries when they occur in the training data? If you look into the machine learning literature, you'll find a lot of strategies, or three strategies for doing that. Either rely on the robustness of the machine learning model to treat or handle noise, on the robustness of it, or use a removal-based strategy where the algorithm will identify those entries and then they will remove them. Or we use a correction-based strategy where the algorithm would correct the label value of those contradictory entries. So this is exactly why I'm here today. I'm here to share with you insights into the results of a study that I've been working on for quite some time now to explore the effectiveness or examine the effectiveness of different class noise handling strategy in the context of build outcome prediction and continuous integration and code quality issue prediction. And the first research question that we raised was, what is the impact of applying class noise handling on the prediction of build outcomes using machine learning-based method? So say that we have a machine learning-based method that we train on historical code changes of code and build outcomes of pass and fail. And then we want to feed this data to train the machine learning model. So the question is, okay, how do we handle noise here? Which strategy is most suited for handling noise before we train the model? And once we apply that class noise handling algorithm, then the model can predict maybe which build will pass or fail in a better way. And the second research question that we had was also about the prediction of code quality issue using the same machine learning-based methods as in here. So we implemented two controlled experiments to answer these two research questions, where the independent variable or the treatment was the class noise handling algorithm. We used three variations of class noise handling algorithms. So these are the consensus filter, majority filters, and domain knowledge based. And these two algorithms, the consensus filter, majority filters, they belong to the family of removal strategy. And the domain knowledge based, it belongs to the correction strategy for handling noise. So if we apply each variation of these three algorithms to the to both data sets that we collect for the build outcome and the code quality data set. Then if we train a machine learning model on this curated version of the data set, do we get a better predictive performance or not? So for that, we use those four performance measures: precision recall, F1 score, and Matthew correlation coefficients to evaluate the effectiveness of those variations. So the two removal strategies that we use is a consensus filter and a majority filter. We picked those because they're among the most widely used algorithms reported in the literature. They rely on an in symbol of classifiers, three classifiers, decision tree, came nearest neighbor, three models, linear regression model. And based on some voting mechanism, an entry in the data set will be tagged as either noisy or not noisy. And then the correction-based algorithm is called domain knowledge base. It's an algorithm that we previously designed and we tested on test case selection data set. And the algorithm basically, it relabels all lines from the negative labels to the positive labels. So in the case, in the context of code review, it will relabel all disapproved lines to approved if they are contradictory. So again, we have this example from the reviewers. The first reviewer disagrees, he disapproves the code, and the second one approves it. And we end up having this corpus of code changes where half of the lines are disapproved and the other half is approved. And then if we measure the class noise ratio here, it will be 50% exactly, because they're they're evenly split between the two classes. And then if we apply the domain knowledge based algorithm, it will relabel all the lines from the disapproved to make them approved. And then we end up with a class noise ratio of 0% here.
Can I interrupt?
Of course.
Please explain this. I fail to understand it. How you change the disapproved to approved even when you apply it. I mean, yeah, so the reviewers are complex, so to say. So by doing this, you introduce a risk into your thinking. I mean, the result.
Of course, I mean, there's a trade-off here. I mean, it's just based on the assumption that, you know, problematic lines of code usually occupy a smaller proportion in the overall code. So we give more weight to those, you know, approved than the disapproved ones in that sense.
I would have expected the class noise to be something below 50, say 20% or something like that. So I get that. But this is quite hard. I mean, 0 is absolute.
Yeah, I mean, in this example, it is 0 because there are no contradictory entries here. All the lines, they're labeled with approved. But you're right. I mean, if you take this in a bigger example, then yes, that's probably right.
Okay, thanks.
And then for the research design, we started the two experiments by collecting the data sets. So to answer research question 1, we collected 49,000 history build job records and their code changes from 110 Java projects. And to answer research question 2, we collected 55,000 code review comments and code changes from 15 Java projects and 1 Python project. And then we applied the bag of board model to extract features from those code changes. And then we needed to generate experimental subjects to run some statistical tests and also to apply the treatments on. So we used the tenfold stratified cross-validation here for that. And then we used a random forest classifier to train the curated or the data set that was exposed to the treatment and before it was exposed to the treatment. And for the analysis, we measured the impact of each of those algorithms on the 4 dependent variables for each individual project. So we looked at how the class noise ratio changed before applying the treatment and after applying it, and also how the precision, recall, F1 score, and MCC changed as well. And then we calculated descriptive statistics to get an understanding of the effect size of each algorithm. And we run some statistical tests to get to answer to see if there is any statistical significant difference between those dependent variables. Yeah, so what you see here are scatter plots that represent improvement trends after applying each algorithm. So we're a bit surprised to see these results because we can see some downward trends here. You can see those lines going in a diagonal fashion, which means that the precision actually deteriorated after applying those class noise handling algorithm, unlike what we expected from the beginning. So that was an interesting observation that we drew here in this build outcome prediction data. And then if we move on to look at the recall trends, we see some improvements in the MF and CF to be more prominent than the DB. So all the algorithms actually improved the DB to some extent, but the CF and MF were more consistent because they could improve more, the recall more in more study subjects. And if you look at the F1 score improvement trends, we see a very similar trends to that we captured in the recall, where the MF and the CF were more consistent than the DB again here. Now, if I turn to report the improvement trends in the second experiments, which is for the code quality issues, what you see here is also correspond to this is for the MCC, sorry. So yeah, with the MCC, using any of those three algorithms would consistently reduce the MCC. So they are consistent, but in an opposite directions, they still reduce MCC and not do any improvements on it.
But you do reduce the noise.
Yes, if you see here, if you look at the red dots here, you see that all of them are placed somewhere along but except the CF. If you look at the CF and the CF, it doesn't do that.
Yes. Yeah, correct. Thank you.
And then to summarize the impact of those three algorithms on the build outcome prediction, we calculated the mean scores of the dependent variables before and after applying each treatment. And what we observe here is that a recall improvements when using all the algorithms, the three algorithms. You see all the bars, the orange bars for the recall. The F1 score slightly improved for the MF after applying MF and CF, but it did not change, or it did still. No, it didn't change much with the DB. The MCC decreased by 7% with MF and CF and decreased by 1% when using the DB algorithm. And then we ran this Mann-Whitney test to see whether there is a statistically significant difference between the precision recall F1 and MCC before and after applying the treatment. And from the table here, we can observe that we have a statistical significant difference in recall F1 and MCC, but not in precision. Now, if we turn to look at the results, the improvement trends for the second experiments, now we see the precision improvement trends here. We see that precision improved the most with the MF after applying the MF algorithm. The improvement appeared for 15 out of 16 study subjects. And then the CF improved 14 out of 16. And the DB came last here with 11 out of 16. 11 out of 16 subjects did not improve with the DB at all. They almost, you can see that the horizontal lines going for the DB here. So only CF and MF consistently improves the precision in the second context. Now, if we look at the improvement trends in recall, we observe that applying MF consistently improves the recall, while CF and DB are not as consistent as MF. And from the F1 improvement trends and the figures, we observed that only the MF and CF algorithms could actually consistently improve F1 score, whereas the DB reduced it, as you see here. So the improvements with the DB was only for 5 out of 16 subjects, compared to 12 and 15 for CF and MF. And when it comes to the MCC, both the MF and the CF, they showed an improvement in the MCC measure in the majority of subjects, with 15 out of 16 subjects improved after applying the CF, and only 7 out of 16 subjects improved when using the DB. If we look at the mean performance scores now, you can see that the precision, all of the dependent variables, they increase when using the MF and CF, but they did not pretty much change when using the DB algorithm. So DB basically had no effects on precision and MCC, and the others, the MF and CF, they led to an improvement with respect to the 4 dependent variables. And if we look at the Mann-Whitney test results, we also see that CF and MF have significant impacts on precision, recall, F1 and MCC, and DB is not statistically significant at all with respect to those 4 variables. In conclusion, from experiments 1, we conclude that irrespective of which algorithm we use to handle the data, we'll only get an improvement in recall and F1 score, but MCC will decrease, and so does precision. The conclusion from experiment 2 was that using CF and MF will improve all the performance matrix across the board, but DB had no effect at all on neither of the 4 performance measures. The future work, we plan to investigate further different software engineering data to see how those algorithms apply and how they improve the predictive performance of the model. We also want to investigate the effects of another type of noise called attribute noise, because this study only focused on class noise. There's other type of noise called attribute noise. And yeah, maybe we can also explore whether other algorithms that exist in the literature can yield better improvement in these 2 contexts. So thank you very much. With that, I finish my presentation.
Can you go back, please?